Hello, hello. We are currently dealing with changes that matter undergoes, and more specifically, physical processes. In previous lectures, in this particular series, we covered the basic heating and cooling of matter, as well as ideal gas changes of state. Now, in this talk, we'll look at changes of state when matter changes its phase between gas, liquid, and solid. In this lecture, we're looking at phase changes. We start with bulk matter in an initial phase state, solid, liquid, gas, at constant pressure. Add energy, an endothermic process, or take away energy, an exothermic process, from the matter, and end with the result where we have turned the bulk matter into a different phase state, solid, liquid, gas. All the common conversions between the different phases of matter are pictured on the slide on what is called a heating curve. The curve shown begins with a solid piece of matter of a certain mass at low temperature, and then we measure the temperature changes, the y-axis, and the added heat to the system, the x-axis. Along the way, changes in the phase of matter will occur. So in this pictured heating curve for a compound, the sloped areas are where we simply heat up the matter, either in the solid, liquid, or gas phases, and change the matter's temperature without changing its phase. The slope of these lines is determined by our old friend, the heat capacities. Remember, the heat capacity is the property of the matter which governs the changes in temperature for an amount of matter with given energy input. The greater the heat capacity, the smaller the slope. The flat areas where the slope is zero are called first-order changes of state, and this is where changes of the phase are occurring. In these areas, as we add heat to the system, the temperature doesn't change as long as two phases coexist. But once all of the matter has converted to one of the two phases, then it moves on past these phase changes, and the single-phase piece of matter begins changing temperature again. Water, for example, at its boiling point, does not change temperature. It stays right at about 100 degrees Celsius the whole time liquid water is present. But as we add heat, more of the liquid is converted to a vapor or gas. We also call the water gas steam. Once the liquid water is gone and completely converted to steam, then the temperature rises again. Water can only get to 100 degrees Celsius maximum in normal atmospheric conditions, but steam can continue to get hotter as we add heat, reaching temperatures well beyond 100 degrees Celsius. That's why steam can be very dangerous, and the steam burns can be much more severe than hot water burns. So remember, for the first order change of state where two phases are present, the temperature remains the same, even as heat is added or lost in the system. Now, as we continue to look at the heating curve, we see that it has two first order phase change regions. Solid to a liquid phase change we call melting or fusion. The reverse direction is called freezing. The second region is the liquid to a gas phase change that is called vaporization or boiling. The reverse direction, gas to liquid, is called condensation. Our goal in this next example is to produce the heating curve of a compound from a low temperature solid to a high energy, high temperature gas, calculating the energy at each step and region of the heating curve. The compound we'll work with is water. Let's produce a heating curve beginning with ice at minus 50 degrees Celsius, taking it all the way to a steam at a temperature of 150 degrees Celsius. The vital data we need to produce the heating curve for water is on the table. Be aware that for this example, the specific heat capacities and heats of phase transitions are per gram of matter and not kilogram or moles. It is common to find values that are in a variety of energy and mass units. We're going to begin by starting with 100 grams of H2O solid ice at minus 50 degrees Celsius. Ice doesn't melt or freeze until we get to 0 degrees Celsius. So we're going to heat up our ice from minus 50 degrees Celsius to the melting temperature of 0 degrees Celsius, a 50 degrees Celsius or Kelvin change. We did this kind of computation in the previous lecture. All we need is the specific heat capacity of the ice, which from our data table is 2.06 joules per gram Kelvin. We can calculate the energy we need to do the job by multiplying the mass of the ice times the specific heat capacity of the ice times the temperature change. All the units cancel, leaving us with just joules. The energy it will take to raise the temperature of the ice from minus 50 degrees Celsius to 0 degrees Celsius is 10,300 joules or 10.3 kilojoules. The values should be positive because we're adding heat to the system and the temperature change is positive. If we're cooling the system, the energy value would have been a negative quantity. Now, we're going to add energy until we melt all the ice. Melting is also called fusion. Fusion is an old word that means melting together. If we were going the other way, doing an exothermic cooling of liquid water to ice, the process would be called freezing. To calculate the energy, we need a quantity that is unique to the water called the latent heat or enthalpy of fusion, which is the energy needed per gram or mole of a substance to melt it. For H2O, this value is delta H fusion equals 334.16 joules per gram. The mass in the denominator should make sense. The more ice we have in grams, the more energy it'll take to melt it. To calculate the energy needed to melt the ice, we simply multiply the latent heat of fusion by the amount of ice we have. To melt 100 grams of ice, it will take 33,420 joules or 33.42 kilojoules of energy. The energy, as before, is positive because we're adding energy to the system. To plot these two steps on the heating curve, we start at minus 50 degrees Celsius. It takes 10.3 kilojoules of energy to get ice to 0 degrees Celsius, and then we add an additional 33.4 kilojoules of energy to melt the ice. Remember, we don't change the temperature during a phase change, so we have put a total of 43.7 kilojoules into our system to get to liquid water at 0 degrees Celsius. Let's keep going. We now want to heat our liquid water from 0 degrees Celsius to the boiling temperature of 100 degrees Celsius. Again, this is heating of bulk matter, which requires the use of the heat capacity for liquid water. We see that the specific heat of liquid water is 4.184 joules per gram Kelvin on the table. To make the calculations easier using heat capacities, we usually assume the values do not change in this temperature range, thus are constant. The product of the mass, the specific heat, and the temperature change of 100 degrees Celsius or Kelvin gives us a total energy value of 41.84 kilojoules needed to heat the water from 0 degrees Celsius to 100 degrees Celsius. Now we boil the water. Before doing that, let's remind ourselves what the boiling or vaporization process means. We first define a quantity called the vapor pressure of the liquid. Let's look at the liquid water at the surface layer. Just above the surface of the liquid is a layer of water molecules that have escaped the hydrogen bonding of the liquid and moved into the gas phase. The gas pressure just above the surface is the pure vapor pressure of the water, since at this immediate layer, the gas phase is mostly water molecules. The atmosphere above this gaseous water layer acts as a lid of higher pressure, keeping the water vapor contained close to the surface of the liquid. As we heat up the water, more water molecules escape from the surface because of the added kinetic energy to break the intermolecular forces of the liquid. This continual heating increases the vapor pressure of the water just above the surface. Still, the water is contained by the atmospheric lid. The increase in the vapor pressure carries on until we have added enough energy and the temperature of the water has gotten high enough for the vapor pressure at the surface to be equal to the atmospheric pressure. Once this happens, the water vapor busts through the atmospheric lid and H2O molecules can freely escape the surface of the liquid. We see this as bubbles. So in short, the boiling point is the temperature at which the vapor pressure of the liquid is equal to the atmospheric pressure above it. For our system, the atmospheric pressure is around 1 atmosphere. So at the boiling point of 100 degrees Celsius, the vapor pressure of water achieves an equal vapor pressure, 1 atmosphere. As we learned before, the stronger the intermolecular forces of the molecules in the bulk matter, the higher the boiling point temperature will become. At higher altitudes like Denver, Colorado, or Mount Everest, where the atmospheric pressure is considerably less than where I'm at in North Carolina, we don't have to heat the water as much to get the vapor pressure equal to the reduced atmospheric pressure at this higher elevation, and to make the water boil. That's also why it takes longer to boil an egg or make spaghetti at higher elevations. The boiling water is just not as hot because it boils below 100 degrees Celsius. The opposite process, where we cool the system so that the vapor phase transitions back to the liquid phase, is called condensation. So let's continue with our heating curve. To calculate the energy of vaporization or boiling, we need a quantity unique to the water called the latent heat of vaporization, which is the energy needed per gram or mole of a substance to vaporize it. For H2O, this is 2,259 joules per gram in our table. As before, the mass in the denominator should make sense. The more water we have in grams, the more energy it will take to vaporize it. To calculate the energy needed to boil the water, we multiply the latent heat of vaporization by the amount of water we have. For 100 grams of liquid water, it will take 225,900 joules or 225.9 kilojoules of energy to boil off the water. This value is the greatest amount of energy we have calculated yet. Remember that H2O is one of our examples of a system that is held together by strong hydrogen-bonded intermolecular forces. It takes a lot of energy to break this force between water molecules. To finish up, take the steam we've made at 100 degrees Celsius and continue heating it up to 150 degrees Celsius. Again, we point out that steam can exist at much higher temperatures than hot water. Using the specific heat capacity for steam, 2.02 joules per gram Kelvin, we take the product of the mass of steam, 100 grams, the heat capacity, and the temperature change, which is 50 degrees Celsius, and get the energy input of 10.1 kilojoules to heat the steam from 100 degrees Celsius to 150 degrees Celsius. We will draw these last 3 steps on our heating curve. At 0 degrees Celsius of water, we've already put in 43.7 kilojoules of energy. Now we've added the 41.8 kilojoules of energy it took to heat the water to 100 degrees Celsius, the 225.9 kilojoules it took to boil the water and make steam at 100 degrees Celsius, and finally, the 10.1 kilojoules it took to heat the steam to 150 degrees Celsius. Adding it all together, it took about 321.5 kilojoules of energy to take 100 grams of ice at minus 50 degrees Celsius to 100 grams of steam at 150 degrees Celsius. There are some instances where a compound may forego a liquid to gas vaporization and go from a solid directly to a gas. When a substance goes from a solid to gas, bypassing the liquid phase, we call the process a sublimation. The classic example of this behavior is CO2 or dry ice. The physical property data for CO2 is shown in the table. As we did before, we can create a heating curve for 100 grams of dry ice at minus 100 degrees Celsius, well below its sublimation temperature, and take it to CO2 gas at room temperature, a comfy 25 degrees Celsius. Again, as we did before, we will heat the dry ice from minus 100 degrees Celsius to its sublimation temperature, minus 78.5 degrees Celsius. The 0.124 kilojoules of energy needed to get the job done is the product of the mass of CO2, the specific heat capacity of the dry ice, and the temperature change. Now we turn the dry ice to CO2 vapor. The The latent heat of sublimation is the energy per gram or mole of a substance required to sublime it. For dry ice, the latent heat of sublimation is 734 joules per gram, which we multiply by 100 grams of CO2, giving us 73,400 joules, or 73.4 kilojoules needed to sublime the 100 grams of dry ice. Finally, we heat up the CO2 gas to 25 degrees Celsius and calculate the energy by using the specific heat capacity for the CO2 gas multiplied by the temperature change and mass. To take the CO2 from minus 78.5 degrees Celsius to 25 degrees Celsius will take about 7.97 kilojoules of energy. From the data and the computations on the previous slide, we can generate the following heating curve for CO2 at 1 atmosphere. Well, that will do for now. To practice producing heating curves, just pick a common chemical and take a certain amount of the material at a temperature well below its freezing point, and compute a heating curve that will take it to its gaseous state at a temperature above its boiling point. All you need are latent heats and heat capacities, and you should find much of what you need doing a web search or by using the handy website set up by the National Institutes of Standards and Technology called the NIST Chemistry Webbook. The NIST webpage is on this slide and also in the acknowledgments. I find much of the thermodynamic data I need at this site. Well, hope you have a terrific day. Catch you later.